Hello everyone. In this lecture, we are going to see ASME, Section 8, Division 1, Subsection A, UG 32, Example Calculation of Thickness of Hemispherical Head. Our flagship course is Master Static Equipment Design and PVElite and Master Welded Storage Tank, as per API 650. We have curated courses to suit your learning needs, so do visit our learning platform on scutoid.thinkific.com.
Okay, so let us talk about hemispherical head. Very simple. But making hemisphere is not that simple. Okay. We need to see, just making this by formings, it's very, very difficult. Okay. If you just want to make completely like we make typically 2:1 or ellipsoidal head, 2:1 or tori-conical. This hemispherical heads, it's very difficult if we just try to form. So what we do crown and petal formation, like you see in the figure. Okay. So it will be made in crown and petals. Crown is the topmost part. You can see that round one. In the left hand side figure, it's the bottommost, okay, the circular portion. And these are the petals. Okay. So crown and petal formation. Okay. So this is how typically you will see of hemispherical dish. Okay. When we use hemispherical head, when your pressure is very high, okay, in that case, you can save lots of material. Okay. So typically you will see that in bullets, mounted bullets, where the pressure is really high. Okay. So you can see here crown and petals. Now, this is a typical hemispherical head. D here is the internal diameter. L is the inside spherical or crown radius, as we call them in tori or 2:1. Okay, spherical or crown radius. In this case, it's very simple. It's just the half of the diameter, right? T is the thickness of the head. Okay. And okay, so now the condition is, if to apply the formula which is given in UG 32E, we need to meet these conditions. Thickness should be less than 0.356 times L. Pressure should be less than or equal to 0.665 SE. So before doing the calculation, try to calculate these values, and you should always mention these conditions in your calculation report. Okay, if your software is not doing this calculation, you have to add, because we have to check this condition. Okay. So inside spherical or crown radius, very easy for a spherical, just half of the diameter. Okay, because it's circle finally. Okay, so this is the formula. PL divided by 2SE minus 0.2 P. Okay. L, we know that's the radius of this sphere. Okay. Now let us do quick calculation for a typical hemispherical head, so that you will be clear with the calculation also. If any doubt is there, we can solve it in this. Okay. Material of construction 516 grade 70. Internal design pressure 2 MPa. Temperature 250, inside diameter 2000, tan to 10 length also 2000, corrosion lance 3 mm. Okay. Allowable working stress 138. Joint efficiency 1. Now there is liquid, and the depth of the liquid is 1000 mm. Okay, and the specific gravity of this fluid, density of the fluid is 0.8. So first of all, I'll have to start with the static head calculation. So static head, we know rho, G, and H dash, which is the height of that liquid. Rho is the density. We know it's 0.8. And if we multiply with the density of water, we'll get the actual density of the fluid. So 800 kg if the specific density is 0.8. G 9.81, H dash is 1 meter, okay, because the height of the liquid is 1 meter. Now, if we put all this value, you will get the static head, okay, which is nothing but 1 meter. So finally, what value we got for static head? 0.008 MPa. Okay, this is my static head. Now I'll add this static head in the internal design pressure. My internal design pressure is 2 MPa plus 0.008, 2.008. Okay. Now we'll do the thickness calculation. Pressure we know 2.008 L, 1003, because it's the inside corroded radius. Okay, remember that. So we have removed corrosion allowance, and because of removing corrosion allowance, your radius will increase, and that is the reason it's 1003. Okay, rest of the thing, you know, 2S E 0.2 into P. Okay, thickness which we get by using this calculation is 7.31. Okay, it's in mm, 7.31 mm. Now I'll have to add corrosion allowance in this thickness. So finally, after adding the corrosion allowance, I got 10.31. So this is my design thickness. Okay. Now I need to find nominal, because I need a plate with which I can fabricate, and I need that plate in the market, you know, which is available directly. So 12 mm, can I take? If I'm taking 12 mm, is it correct for 10.31 for a hemispherical head? Himanshu is saying 14 preferable. Anand is saying yes. What about others? So if you are going with the logic that 10% thinning, then also you can use. And if you remember, it's basically a crown and petal construction. Okay. So thinning will be very, very minimum. So definitely you can use 12 mm, because it's the depth is not going to be forming depth is not coming into picture. So you're finally, the forming is very, it's not that critical. So you won't get lots of fiber elongation. Okay. So 12 mm I selected. Okay. Now, okay. Now there's a typical case. Okay. I'm just creating one scenario. In the same calculation, I got the shell thickness as 18 mm. Okay. So dish end, what we got? Dish end we got 12 mm. For shell, we got 18. Okay. Now I need to join them. Okay. Can I join like this? Akash is saying taper. So, okay, I'll provide the taper. Okay, I'll provide the taper. So if I'm providing the taper, can I join like this, whatever we have indicated? So 1:3 taper, Lagamanna is saying no. L is greater than equal to 3y. Okay, so that is same 1:3 ratio, Himanshu. 1:3. Outside will be flush. So this is the taper which I'm making. Can you see the pointers? Like this, 1:3 taper I provided. So I provided 1:3 taper like this. Is it okay? So Vivek is saying yes. What about others? If I provide taper, like 1:3 you are saying. So I'm saying, okay, I provided 1:3 taper like this. I grinded the shell, and now it's 1:3 taper. Okay. So Fazil saying not sure. Akash is saying yes, I can provide. SM is saying ID should be matched. Okay. Okay. Himanshu is saying taper as UW 13.1. Okay. So see, I am trying to maintain that taper. If you see UG 13.1, there is requirement of offset condition and taper. I'm meeting that, let us say. What is grossly wrong in this? I'm saying it's, as a designer, even if you forget about taper and all, it is a completely no-no. So someone is saying ID should be matching. Okay, if I match the ID, okay, I just shift it and match the ID. Now it is acceptable. Lagamanna. When you will hear the answer, there won't be any doubt. Now Anand is writing thickness of the shell will be less than the design thickness. Not acceptable. Anand is absolutely right. Okay, and the same thing was spoken by Sanjay ji, and I think Ajay was also trying to mention. So guys, finally, whatever is there in this side, after this straight portion from where it's starting, the straight portion will always be designed as cylinder. Okay, and if it is a cylinder, the thickness requirement will be 18 or it will be 12. Can I have less than 18? If 18 is my nominal thickness, okay, can I have less than that? You will say, oh, I can go up to design, but by reducing it may even go, you have to match with 12. Okay, and see the descent portion is coming in the straight portion. This descent is having a little bit straight face, which is 12 thick. Do you think it's acceptable? First of all, are you, all of you agree to that this cannot be accepted? Forget about OD-ID match. How will match will see? We are going to see if there is difference, how we can connect. But basically, as a designer, okay, now SM is talking about cutback, right? We'll come to that. So see, basically, do you realize there is grossly wrong? Whatever we studied, it's completely violating that. It is not at all acceptable. Okay, as a designer, straight away will say that in the straight portion, I cannot have thickness less than the cylinder design thickness formula. Okay, so what to do? If the shell, if the descent is going to be welded, even if I reduce this small straight portion, if the shell is starting directly from the straight point, then again you will face problem of tapering. How to do the taper? So you'll have to grind again at the junction. You will have lesser thickness, so stresses will be more. So what to do? Okay, so the solution is cut back length. Okay, so please remember, your hemispherical head, unlike your 2:1 or torus spherical, there is no straight portion. There is no skirt. Okay, there is no straight face in the hemispherical head. Always remember that. Okay, now what we will do? How we'll join? Let us try to understand that now. Okay, great. So let us try to understand the cutback length concept. Okay, so this is how we were trying to join. Okay, even if I connect exactly up to the hemispherical portion, exactly I have maintained that hemispherical head and I'm just connecting the shell. Okay, so how I will make this? This is the shell head. I think you can identify. Okay, so as per UW, you were saying like OD to be matched, ID to be matched. The code requirement is the center line distance of these two elements shall be less equal to the thickness difference, half of the thickness difference. Okay, UW 13.1. Absolutely, Anand. So this is the requirement. Okay, code does not say that ID or OD to be matched. Center line has to match with this limitation. Okay, this is the code requirement, but still my problem is not solved. Okay, gap I have created, but now can I leave this much thickness? Just offsetting. I need to do taper. Okay, this is the gap. Now, what to do? Okay, how I'll try to overcome this problem. So now what we are doing, let's see this figure. We have just extended this line, okay, ID of the shell, okay, where it's touching to the addition here. Okay, hope you can see. Okay, now once this extension is done, at this point, I will cut that portion of the addition. That is the reason it's called cut back. I have extended this cylinder portion up to the addition and cut that portion. Making sense? Now, what I'll do, I'll just see this concept is actually cut back length. Now, see, I cannot have this much gap, right? So how I'll fill this gap? Increase the shell length. Whatever cutback length we had, I'll increase the shell length to match. Now, once I have matched that, I'll taper it. You wanted always to taper. Now it's tapered. Okay, and the taper is now located within the addition. Okay, this is the tan to tan line. It's located here. Okay, so now from here your straight portion is starting, and you will not have any problem in the thickness of the cylinder. Whatever thickness we are getting, it's the addition, and we are having more than the required thickness of what addition we are having. Okay, so this is how your additions are connected with shell. So this calculation you have to do while preparing the drawing. Okay, this is done when preparing the drawing, and you need to have this length, okay, extended, and make the shell with this extended length. Otherwise, your vessel will have to be shortened. Okay, if you forgot to add this length, overall vessel length will get shortened, because for matching you have to cut back your addition. Is it clear to everyone? Is it making sense? Akash, yes. Yes. Himanshu is saying one question. Please go ahead, Himanshu. The processor is no, Ajay, this processor is not there in code. This is based on, so code will just say that you have to maintain the thicknesses. Now it's here your engineering judgment comes into picture. Okay, so when people made, then they realized that there's a problem, and then they corrected that.
For in-depth training and to learn more about these courses, register with the link in the description.